We start our discussion on the module 1 of chapter 3 now. The main object of discussion in this chapter are certain special kinds of functions. We have come across some special kinds of sets, namely Lebesgue measurable sets already in the last 2 chapters, and we intend to define certain functions which are related naturally to these measurable sets. Now recall that in many of these concepts, the sets arising out of the functions are more important than the values of the functions. For example, you already know the definition of continuous functions. A function is continuous if and only if the inverse image of an open set is an open set. So, here also we will specifically concentrate on the inverse images of the functions. So, we will see that a function is measurable if and only if the inverse image of a measurable set is measurable. We will give the formal definition later, but before that we need to again know why we need these types of functions. So, with this we go to the first slide. So, let us see why we need measurable functions. We ultimately intend to define an integration process modeled on Riemann integration, which should be stronger than Riemann integration. What we did in Riemann integration? We had integrated bounded functions defined on closed interval a b. Now, instead of interval, we now have measurable sets, because in the Riemann integration we used the lengths of the intervals to define the upper sums and lower sums and finally the value of the integral. So, we can use the measures of sets instead of the lengths. So, naturally instead of only intervals, we would like to integrate functions defined on measurable sets and see that functions are the objects which we integrate. So, while in Riemann integration we integrated bounded functions, here we need to introduce certain functions which we will ultimately integrate. These are precisely measurable functions. So, we need to define a special class of functions which we will like to integrate. So, we go to the formal definition of a measurable function. Let f d to r be a real valued function defined on a measurable subset d of r. Then f is called Lebesgue measurable, or more briefly we will just say that it is measurable if one of the following holds. For any alpha belonging to R, the set x belonging to D where f x is greater than alpha is measurable, or collection of all x belonging to D where f x is less or equal to alpha is measurable for any alpha belonging to R, or collection of all x belonging to D f x less than alpha is measurable for any alpha belonging to R, or the last condition, collection of all x belonging to D where f x is greater or equal to alpha is measurable for any alpha belonging to R. Now, we can easily see that these 4 conditions are mutually equivalent. See that for any alpha belonging to R, open alpha infinity complement is the interval open minus infinity alpha closed, whereas open interval minus infinity alpha, its complement is closed alpha infinity open. On the other hand, see that we can write open interval alpha infinity as countable union of these types of intervals, union n equal to 1 to infinity closed alpha plus 1 by n infinity open. And finally, closed alpha infinity open can be defined as intersection n equal to 1 to infinity open interval alpha minus 1 by n infinity open. Since measurable sets form a sigma algebra and you all know that set theoretic operations remain invariant under inverse mapping. So, the assertion that the conditions 1, 2, 3, 4 in the last slide are equivalent just follows from the fact that measurable sets form a sigma algebra. So, when we will try to show that a typical function is measurable, we will have to show only one of the 4 conditions. Now, one natural question arises that the measure takes the value infinity, and here also we could have considered extended real valued functions, that is functions which also take the value minus infinity or infinity. For example, if we consider the function 1 by x, then its value at the point 0. When we consider extended real valued functions, then in addition to the above mentioned properties, we also need to have 2 more properties, that f inverse of singleton set infinity and f inverse of singleton minus infinity must also be measurable. But throughout we will not deal with extended real valued functions, because whatever results we will prove with real valued functions can easily be extended to the extended real valued functions, and we do not need more complications also in our proofs. So, we start with the theorem 1, which states that if f, g are 2 measurable functions and c is a given constant, then Cf is measurable, f plus g, f minus g, f square, mod f, minimum of f g, maximum of f g, all these functions are measurable. And if you see the properties more closely, see that when we say that Cf is measurable and f plus g is also measurable, this means that the collection of all measurable functions form a vector space over the set of real numbers with respect to the usual addition of functions and scalar multiplication of functions. So, it forms a linear space. We start with the first proof. If C equal to 0, then the function CF is the constant function 0, and the result is obvious, because it is quite trivial that every constant function is measurable. Now, let alpha belonging to R be given. If C is positive, then collection of all x belonging to D, where CFX is greater than alpha, is equal to the set collection of all x belonging to D, where Fx is greater than alpha by C. If C is negative, then collection of all x belonging to D, where CFX is greater than alpha, is nothing but the set x belonging to D, where Fx is less than alpha by C. But see that already by our assumption f is measurable, and so the sets on the right hand side are measurable, and this shows that the scalar multiple CF is also a measurable function. We will now show that if f and g are measurable, then their sum function f plus g is also measurable. For this, we start with a given real number alpha belonging to R. We consider the set x belonging to D, for which Fx plus Gx is greater than alpha. Now, see that Fx plus Gx is greater than alpha if and only if Fx is greater than alpha minus Gx. Now, recall that the set of rational numbers is dense in the real line, and so between any two real numbers we can find a rational number R. So, Fx is greater than alpha minus Gx happens if and only if we can find a rational number R such that Fx is greater than R greater than alpha minus Gx. So, the set x belonging to D, where Fx plus Gx is greater than alpha, can be written as countable union, where the union runs over all rational numbers R, and we take the two sets x belonging to D, where Fx is greater than R, and x belonging to D, where Gx is greater than alpha minus R, and we take the intersection of these two sets. Now, see that f and g both are measurable. So, within the bracket both the sets are measurable, their intersection is measurable, and finally, we are taking countable union of measurable sets. So, the final set is also measurable. So, this shows that collection of all x belonging to D, where Fx plus Gx is greater than alpha, should be measurable, and we have proved that the function f plus g is measurable. Now, we will prove that for a function g minus g is also measurable. Now, this is quite clear, and it follows from the assertion 1, because we can write the function minus g as minus 1 into g. So, since g is measurable, so its scalar multiple minus 1 into g is also measurable. Now, see that if f is measurable, g is already measurable. This implies that if we consider the difference function f minus g, we can write f minus g as f plus minus g, and so this is also measurable by our assertion 2. Next, let alpha belonging to R be given. We consider the function f square. So, if we consider the collection of all x belonging to D, where f square x is greater or equal to alpha, then this set is equal to D when alpha is less or equal to 0, because the square cannot be negative, and collection of all x belonging to D where f square x is greater or equal to alpha, this is equal to collection of all x belonging to D where f x is greater or equal to root alpha union collection of all x belonging to D where f x is less or equal to minus root alpha if alpha is positive. Again, since f is already measurable, so both the sets on the right hand side are measurable and their union is measurable. So, this shows that f square is also measurable. Finally, see that if we consider the product function f g, then the measurability of the product function f g follows from all the above results and the fact that we can express the function f g in this way: f plus g whole square minus f minus g whole square by 4. See that since f and g are measurable, so f plus g and f minus g are measurable. We have already proved that square of a measurable function is measurable. So, f plus g whole square and f minus g whole square are measurable and their difference is again measurable, and finally, we are taking a scalar multiple of that particular measurable function. Similarly, we can show that if f is not equal to 0, then 1 by f is also measurable and maximum of f g or minimum of f g are also measurable. The proofs are given in the course material, and in any case they are quite easy. Now, we go to our next theorem. If f n, n belonging to capital N, is a sequence of measurable functions, then supremum n f n, infimum n f n, lim sup n f n, lim inf n f n and limit n f n, if the limit exists, are all measurable. See that when we have a sequence of measurable functions, always the supremum and infimum exists, as also the lim sup and lim inf always exists, and the limit exists if and only if the lim sup f n is equal to lim inf f n. So, we just prove that the supremum and infimum of f n, these two functions are measurable. So, we start with a real number alpha. See that collection of all x belonging to D where supremum over n f n x is greater than alpha, this is equal to union n equal to 1 to infinity x belonging to D where f n x is greater than alpha. Since each f n is assumed to be measurable, so each set on the right hand side are measurable and their countable union is also measurable. So, this shows that collection of all x belonging to D where supremum over n f n x is greater than alpha, this set is measurable and which implies that the supremum function of f n is measurable. The second assertion follows from the observation that if we consider the infimum n f n, then collection of all x belonging to D for which infimum n f n x is less than alpha, this is actually union n equal to 1 to infinity collection of all x belonging to D where f n x is less than alpha. Again, since every set on the right hand side are measurable by the measurability of f n, so this shows that the set on the left hand side is also measurable and consequently infimum n f n is measurable. Now, from these two assertions, the measurability of lim sup f n and lim inf f n also follow, because just remember the definition of lim sup. What is lim sup? Lim sup of f n is defined in this way. We first take the supremum of all f n, then we take the supremum of the functions starting from f 2, that is f 2, f 3, f n etc. Then we take the supremum of the functions starting from f 3. Now, see that if we take the supremum in this way, that is we take supremum n greater or equal to I f n, then this becomes a decreasing sequence of functions and it is always convergent and its limit is infimum over I supremum n greater or equal to I f n. And since we already know that sup and inf of measurable functions are measurable, so lim sup f n becomes measurable. And similarly, we can show that lim inf of f n is also measurable. Now, see that if the sequence of functions f n is pointwise convergent to a function f, that is limit f n exists, then the limit n f n is equal to the lim sup and lim inf, both are measurable. So, limit n f n is also measurable. See that we have more advantage than continuous functions, say, because you know that if f n is a sequence of continuous functions and f n is pointwise convergent to a limit function f, then the limit function may not be continuous. But when we consider measurable functions, then we have a better result, that if f n is pointwise convergent to f and each f n is measurable, then the limit function f is also measurable. Now, we show a particular result, that let f d to r be a measurable function and let A is the collection of all x belonging to D where f x is equal to 0. Now, if 1 by f is defined to be alpha on the set A for some alpha belonging to R, then we will show that 1 by f is measurable. Moreover, if the measure of the set A is 0, then we will show that 1 by f is measurable irrespective of the values we assign to it on the set A. First, observe that since f is measurable, so the set x belonging to D where f x is equal to 0, since this set can be written as the intersection of two sets f x less or equal to 0 and f x greater or equal to 0. So, this set is measurable and consequently D minus A is measurable. And so, f from D minus A to R is measurable. Obviously, 1 by f is well defined on D minus A and so is measurable. Now, for any real number C, if we consider the set x belongs to D where 1 by f x is greater than C, this is equal to x belongs to D minus A where 1 by f x is greater than C if C is greater or equal to alpha, and this is equal to collection of all x belong to D minus A where 1 by f x is greater than C union the set A where f x is 0 if C is less than alpha. Now, since 1 by f is already measurable on the set D minus A, so each set on the right hand side are measurable, and this shows that the function 1 by f is measurable. In the second case, define g d to r by g x equal to f x when f x is not equal to 0, and suppose g x takes the value beta for all x belonging to A where beta is a non-zero real number. Since the measure of the set A is 0, so obviously g equal to f almost everywhere, and so g is measurable. Now, g is not equal to 0 on D, so 1 by g exists and we know that 1 by g is also measurable. But 1 by g is again equal to 1 by f almost everywhere. So, from the measurability of the function 1 by g, it now follows that the function 1 by f is also measurable irrespective of whatever value we assign to 1 by f on the set A. So, to summarize, what we did in the first module of chapter 3 is that we have defined special types of functions, measurable functions, which are very naturally related to the notion of measurable sets. We have seen examples of those functions. We have seen that these functions form a vector space, and we have seen more importantly that under pointwise convergence measurability remains invariant, and with this we end this module.